Okay, welcome back to part 2 of the lesson on rose curves, but primarily on cardioids. And so at the end of part 1, we were talking about you guys going ahead and answering parts B and C. So we've just completed in part 1 the graphing of the cardioid 2 plus 2 sine theta on the right-hand side over here. And then part B asks you to determine what you think the polar graph for 2 minus 2 sine theta will look like. And so hopefully you've been able to ascertain from the cosine graphs, the two cosine graphs that we drew before, this one being 2 minus 2 cosine. And let me jump back to the previous page. The graph below being the graph of 2 plus 2 cosine theta. A certain pattern. Firstly, that the cosine graphs are positioned around the x-axis, and then the sine graphs are positioned around the y-axis. And then when we have a negative of the trig function, that acts very much like a reflection. And so what you should hopefully realize is that for the negative of the sine graph, sorry, not very well drawn, but for the negative of the sine graph, what we're going to expect is for it to be underneath the horizontal axis. And then I'll take you through very quickly how to graph that on the calculator, just for checking, although the quiz and the test are going to be non-calculator. And so I've opened up a graph. I'm going to go to menu. I'm going to go to graph entry, and I want to graph a polar graph. And I'm going to enter 2 minus 2. Sorry. Just undo that. Try that again. All right, let me add a graph. What I'm going to do is go to menu again. Graph entry is going to be a polar graph, and I'm doing 2 minus 2. Push the trig button. 2 minus 2 sine. And again, when you're using polar graphs, we must use the theta symbol, and there we have confirmation that our cardioid 2 minus 2 sine theta effectively is a reflection over our horizontal axis. Okay, and so we've got that part. So how do the graphs compare? Of course, the cosine graphs are going to be arranged on the x-axis, not really the x-axis, of course, because it's polar form, and the negative of the cosine graph is effectively going to be a reflection over the y-axis, but again, that's not really the y-axis, but the vertical axis. And similarly for sine, the difference with sine, so we have the same rule with the reflection, but for the sine graph, of course, it is on the y-axis. So I'll continue with the same, technically slightly incorrect notation, but it's on the y-axis or the vertical axis. Okay, and so moving along, so we're going to just go down over here. Okay, so next what we're going to focus on is the effect of the constant or numerical value of a in these graphs. And hopefully what you were able to see from the previous graphs is that the sum of those two values, and so it's maybe a little more obvious for us if we look at the trig graphs. The sum of those two, the maximum value over here of 4 indicates the maximum distance from the pole. So remember, in polar graphs we're talking about in a rectangular graph it's the origin, in a polar graph it's the pole, and so the maximum on the trig function is going to indicate the maximum distance away from the pole. And so here you can see that 1 plus 1 is going to give us 2. That's the maximum distance away from the pole. Here we have a distance of 6, which corresponds to 3 plus 3, and here we have a distance of 8, which corresponds to 4 plus 4. Okay, and so now the idea is, on the next part, we are going to give you a rectangular graph, which we're going to figure out the equation for, and what you're going to need to do is match it up to its corresponding polar graph. And so what I'm going to do is just get you started on a couple of clues with the top two graphs, and then have you attempt to figure out which ones match, and I'll come back to you in a little bit. So a couple of things that we want to look out for right away. So let's start off and let's figure out over here where our center line is going to be. That's going to help us figure out what the equation of this graph is. And so you can see that what we have is a center line which is at the numerical value 3. And so the other thing that we can see is that we've got our starting point. And so we start at theta equal to 0. Our start is in fact at 3. And so that's going to be a significant clue for us. This also tells us, of course, that we're talking about the cosine graph, and so we have shifted up 3. We've got the positive, beg your pardon, not the cosine graph, the sine graph. We have got positive, so a maximum followed by a minimum. We have got an amplitude for the trig graph of 2, and so we have got the graph of 3 plus 2 sine theta. The question that we're going to need to answer is which of the polar graphs does that equation match? Let me just focus on this top polar graph here. And one of the clues that we also want to look at with the polar graphs is, of course, this one is positioned around the x-axis, which should tell us that this is going to be a cosine theta graph. It's also positioned on the left-hand portion or the negative portion of the axis, not the negative portion, but negative if you were to compare it to the negative portion of the x-axis. And so by being arranged on the left-hand side, that of course should give us the clue that this is a minus cosine theta polar graph or cardioid. And so these are the kinds of clues that you're looking for as you try to match each of the 6 rectangular functions to their corresponding polar graph. So go ahead using those kinds of clues and see if you can match those, and I'll complete that off screen and come back to you in a couple of minutes time. Okay, and so what you can see is that I've written in for each of the graphs certain of the clues that you want to be looking for that are going to allow you to identify which of the rectangular graphs match the polar graphs. One of the key ones, of course, is if we look at the position of the polar graph, either positioned on the x or the y-axis, I beg your pardon, on the vertical or horizontal, and then on the upper or lower portion versus the left and the right portion. That gives us an indication of whether it's a cosine graph, a sine graph, a positive, or a negative. The other clues that we can use the rectangular graph to figure out where the starting point is, and we can start to match that with the polar graph at theta equals 0 and see if any of the starting points correspond to points on the graph. Additional clues that we're interested in looking at is the maximums of the graph, or rather the maximum distance that we have from the pole, and those of course are going to correspond to the sum of the constant values. In this case, the coefficient of the trig term and the constant term are not necessarily the same as they were in the previous graphs, but nonetheless we're looking for the sum of each of those, and all of those clues should allow us to start to identify these. You'll also see certain of these graphs have got this little tail where they come around on themselves, and you should hopefully be able to see that what those are going to start to correspond to are the graphs that pass in the rectangular form underneath the x-axis. Okay, and so what we should have is, for the first one, this is going to be corresponds to B, the second one corresponds to D, the third to E, then F, then C, and then A. Okay, and now to the final example. Go back to a fit to width and jump ahead. And so what we're going to do in this is the final of the skills that we need to learn for today, and that is to find the coordinates of points of intersection. And so this is essentially solving equations. Points of intersection of a graph are solving an equation. We can do it algebraically or we can do it graphically. Naturally, the issue that you can see here, excuse me, is that we have got an equation in rectangular form and one in polar form, and so part of the strategy is going to be which form to convert into and then which approach to use. And so in this particular case over here, I'm looking at a hyperbola, and over here I'm going to convert that into rectangular form, and in this particular case I'll use an algebraic approach. And so of course r is equal to cosecant is 1 over sine theta. I can then rearrange that as r sine theta is equal to 3. Substitute in the place of r sine theta y, and we now have the horizontal line y equals 3 is the rectangular equation. And what we're going to do at this point is, since we're going to solve this algebraically, all I'm going to do is substitute the value of y equals 3 in the place of the y's in the other equation, and that will allow me to determine the coordinates of the point of intersection algebraically. Okay, and so go ahead and try that yourself, or you can use a graphical approach as well. Okay, and so what you can see here is the algebraic solution. Substituted 3 in, it simplified to a quadratic, factored, solved for x, got 4 as a repeating solution, and then the question asked for the coordinate or coordinates, and so x is 4, y is equal to 3. Here's a graphical representation of it. If you've done it graphically, of course, you run the risk that it might not be as accurate. Particularly here, you can see I've just sketched by hand, and so I've completed the square to identify that this is a rectangular hyperbola. I've gone ahead and graphed my hyperbola. I've graphed my line y equals 3, and what you can see is that the graphs intersect each other at 4, 3, which of course corresponds to the algebraic solution. Okay, and so example 7, same thing. Go ahead and give it a try. You're going to have to make the decision about whether what you want to convert to rectangular form or polar form, and then go ahead and solve for the point or points, coordinate or coordinates of intersection. And so go ahead and give that a try, and then I'm going to do that off screen. And so pause the video, give that a go on your own, and then I'll have the solutions up for you. Okay, and so here we have our solutions. We started off, I converted to rectangular form. Tan theta can be replaced with y over x. Rearrange, and we have the line y equals 2x, or 2 over 1x, rise over run for the slope, no y-intercept. Over here, I'm going to substitute 2x in the place of y. We get a quadratic, x values of 0 or 4. Sub each of those in the place of x, and we get our corresponding y values of 0 or 8. And our points of intersection 0, 0 or 4, 8. If you've chosen to do it graphically, a little less accurate again because you're a little harder to sketch it to scale. In this case, we would have rearranged the equation into standard form, and you realize that it is a parabola that opens down with a vertex at 3, 9. Graph the line y equals 2x, and the points of intersection, which of course I knew algebraically would have been harder to discern graphically, but they're at 0, 0 and at 4, 8. Okay, and that ends part 2.